Okay, you guys, this is now for the permeability lab. So what we have here is our permeameter. So our permeameter is going to help us to determine the hydraulic conductivity of whatever sediment we put inside of it. So what's going to happen is I'm going to fill this empty space where these little porous discs are with this wet sediment that we just made. And what we do is we're going to pour water in through the top. Water is going to flow through this sediment and water is going to flow out of it. And from that setup, we're going to be able to measure the hydraulic conductivity of this sediment. So the way it works is we have this top lid, which is held in place by these 3 screwed-in poles. So first let me take that off. This spring helps to keep everything compressed. Here's an O-ring. This comes off. Okay. So these are just very porous discs to help take up some of this empty space while I put in my sediment. So we'll need to know the internal diameter, or in other words, the cross-sectional area of this disc. So let me get a ruler and figure out what it is. Okay, so first we'll start by measuring the diameter of this inner circle here. It's coming up as 6 centimeters. 6 centimeters in diameter. Okay. Now we're going to introduce our sediment to this container.
How tight should it be?
Tight. So we're just getting these hand tight. That's all I have on me. So we have this faucet that's going to supply water. This water line leads directly to this container. This container is going to fill with water from this end until it reaches this overflow channel. As water reaches this overflow channel, it'll fall down the tube directly into our drain. And down here on this bottom port is where we can open and close to allow water to flow out of this into our permeameter. Once the water flows into the permeameter, it flows down this channel, it's going to fill up this chamber and flow through our sediment, and then out this exit channel down into the drain as well. So first I'm going to allow water to fill this container and flow through our permeameter so that we have a constant stream achieved. Once we have that constant stream achieved, the next step that we need to take is find out what rate of water is coming out of our sediment. If we have the rate, we have the cross-sectional area, and we have the thickness of the sediment, we'll be able to determine our hydraulic conductivity. So to determine the rate, once I achieve this steady state flow of water, we're just going to remove this exit flow tubing, or even take it out of the drain, and lower it into a beaker. And we're going to time how long it takes to collect approximately either 100 or 1,000 mLs of water, in other words a liter, depending on how fast this is. We haven't done this with this sediment yet, so I don't know how much water we're going to expect to see yet.
Yeah.
And by the way, this is closed. So water cannot flow through here, it's just going to fill up this tube. Let me turn it on a little higher. So now I have this port is open, water is continuously coming in, water is continuously flowing out, and we are maintaining a constant head in our elevated water body. Now I'm going to open this channel to allow water to flow through our setup. Okay, we have water flowing, we have a constant head of water at the top, we have all the valves open so water can flow through our sediment stack, which is full of water and saturated, and exit through the bottom. And we have this slow drip. Wait for it. Bam. That's our water leaving the sample. So this is not at all a very conductive sediment. That's very slow. That's very, very slow. If you were dying of thirst, you wouldn't want it to be like that. Okay, so we are going to then time a small volume of water for how much is coming out of here. Something with a nice even number that we can see, maybe something like even just 10 mLs. So let me go get a graduated cylinder that we'll be able to see this very clearly on. Okay, so we collected 2 mLs, and I don't want to hit stop because it might mess this up, but it took 4 minutes and 51 seconds. Can you guys see that?
Yes.
Okay, so now we have our volume of water and the amount of time it took. We can find a rate from that. Okay, so what we need now is we need to know the distance between this head and where our water was coming out of. That's going to be our total change in head. So we can pick any sort of baseline and begin our measurement. For me, the baseline is going to be the inside of this water table. So let's determine how high it is from our baseline to our low point where our water is exiting. So this water is exiting right here at the 35 centimeter line. At 35 centimeters. Now let's see how high it is to the top of our hydraulic head over here. So we have 89 centimeters plus an additional 21 centimeters. So if we add 80 and 20, that's 100, and 9 and 1 is 10. A total of 110 centimeters from our base to the top of this head. So let's talk about how you calculate hydraulic conductivity. To calculate hydraulic conductivity, we go back to the basic discharge formula of Q is equal to KIA, where Q stands for discharge, measured in this case in cubic centimeters per second. K stands for hydraulic conductivity, which is going to be measured in centimeters per second. I stands for the change in head, or in other words, the hydraulic gradient, which is going to be in this case I wrote centimeters, it should say centimeters per centimeter. And then finally we need our cross-sectional area, which is going to be in square centimeters, right? The first one we're going to want to look at is our hydraulic gradient I. So our hydraulic gradient depends on those 2 hydraulic heads that we had when we were doing this experiment. So initially we measured that where the water drains from the permeameter was 35 centimeters up from our baseline. So we have that as at 35 centimeters. And the hydraulic head of the water that was stable and constantly flowing was up at 110 centimeters above our baseline. So that means that difference in height, our change in head, is 75 centimeters. That 75 centimeter change in head was interacting over the thickness of our sediment. And so what I didn't show is when I had to measure the thickness of the sediment, which actually turned out to be a 2 centimeter thick slice of sediment inside of our permeameter. And I found that out when I took it apart, because as you saw, the walls were very much covered in sand. So it was a 2 centimeter thick slice of sediment. So we're going to plug our I value in here, our cross-sectional area, which you'll have to figure out if you know what the area of a circle is, which is pi r squared. Our diameter was 6 centimeters. Pi is 3.14, so r is going to just be 3 centimeters times pi and square the 3. That'll give you our cross-sectional area, which goes here. And our Q is going to be our discharge rate. Our discharge rate should be in cubic centimeters per second. So a cubic centimeter is equivalent to 1 ml. We measured 2 milliliters of water, so that's 2 cubic centimeters, discharging in 4 minutes and 51 seconds. So 4 minutes times 60 will give us a total amount in seconds. Add the 51 seconds, and you'll get a total time in seconds. So it's going to be 2 cubic centimeters divided by that total number of seconds, and that value goes in here. And then you just solve for K. And whatever number you get for K is going to be our hydraulic conductivity in centimeters per second. So I'm going to show you guys what that looks like written out in math form in just a second. So first we're going to solve Q is equal to KIA for K by dividing both sides by I and A, like so, and you get K is equal to QIA. So first let's look at our hydraulic conductivity. I told you to take that 4 minutes multiplied by 60 seconds per minute, and you get 240 seconds. Add in that 51 seconds, and we get a total time of 291 seconds. That time of 291 seconds is how long it took to get 2 cubic centimeters of water out of our sediment, because we said we had a really low hydraulic conductivity, right? It was barely dripping out. Alright, our hydraulic conductivity depends upon this hydraulic gradient that I've written here. That's a 75 centimeter change in head over the 2 centimeter length of our thin chunk of sediment. And then finally we have our cross-sectional area. So the radius of that inner circle of sediment is 3 centimeters. So you have to square it and multiply by pi. For pi I'm just using 3.14 in these calculations. So we continue solving. Let's figure out what this value is. It is equal to 0.00687 centimeters cubed per second. Over here, 75 over 2 is 37.5, and centimeters over centimeters cancels out, so it no longer has units. 3 centimeters squared is 9 centimeters squared times 3.14 is 28.26 centimeters squared. If we combine these two together, I'm not dividing yet because I want to show you how we get there. Combine these two numbers together with multiplication, and we get 1059.75 square centimeters, and we're dividing our 0.00687 cubic centimeters per second by that number. So cubic centimeters per second divided by centimeters squared gives us centimeters per second. And the number that we get is very small, so I've written in scientific notation 6.48 times 10 to the negative 6th centimeters per second. Is that realistic? Let's consult this chart over here. For hydraulic conductivities in centimeters per second, we're at just above 10 to the negative 6 centimeters per second. So right in between clay and silty sand,